So I'll mostly be talking about the kind of models I use, but before that, to restart from where we ended yesterday night or yesterday afternoon. I ended with this slide. And what I meant by these slides, I'm not going to go into the details. I'm not going to tell you about all the theories that you could put there. Basically, all these theories are options for the kind of theories that people have been doing in ecology. Once you accept that you're in this, reductionist point of view of communities where you explain them as the certain composition, species composition, and so on and so forth, right? So once we are playing this game, once we have made the choices that I talked about yesterday, you're in this arena, and now you have a bunch of more or less related ways to go about modeling systems. And I guess, so I want to say two things. One thing I will say at the start of this lecture, and one thing I will say at the end of this lecture. Both of them are a bit in what I talked about yesterday. But the first thing I want to say is, if I am an ecologist, or if I want to understand ecology for itself, what do I get out of, let's say, drawing a graph like that, and then trying to put it in terms of math, trying to boil it down to a mathematical model. And then at the end of my lecture, I'll talk a bit about the thing I mentioned yesterday, which is, if on the other hand, I'm a mathematician or a physicist, and what I care about is doing interesting physics or interesting mathematics, what do I get out of doing ecology, right? So already talked about a bit, but to start with, first point I want to make is, okay, all the points on this cube, and I'm not going to explain what they are, we could talk about it for a while, but every point on this cube typically has its own models, its own literature, its own ways of doing things. Let's say you have neutral theory would be here. Species distribution models might be here. A simple predator-prey model might be here. A simple model of spatial spread of invasions of an invader in space would be there. And you're not going to write the same equation usually in those cases. Now, one thing that's kind of nice, and the reason why I was saying, in some sense, generalized Lotka-Volterra plus space plus noise gives you all the basic questions that you could ask in this cube, in this space, is you could get all these different behaviors as certain limits of a generalized Lotka-Volterra with space with noise. Just to give you one example, which I think is going to be hopefully quite intuitive after the lectures from Jacopo and from Vishwasha, is that neutral theory, you can almost map it to a GLV, to a Lotka-Volterra. So neutral theory in its original form, as you saw, is a discrete birth-death process with certain parameters and whatnot. In some limits, it's morally equivalent to a continuous Lotka-Volterra where all the interactions are the same. And when there is this demographic noise, which is proportional to the square root of the abundance. And you could go through everything that we saw this morning and yesterday morning, maybe, to say that, okay, except in some limits when the populations are very small or when one species is completely dominant, in most of the bulk, those two models are going to say roughly the same thing. And that's a bit of what I mean. They will allow you to ask the same questions. They will tell you about the same phenomena, right? So in a sense, if you could do this for every theory on this cube, you would be able then to say, okay, if I put them all in the same language, what are the different parameter limits in which I would get one rather than another? And that's something that is interesting because those axes that are very verbal, right? So those are very conceptual axes. I understand a bit what they mean, but they're still a bit hazy. They could be debated. Once they just become parameter values, you could, in principle, hopefully measure those parameter values and know where you are. So I guess that's kind of what I want to say, that if you take this model here, which is you have your environment, your interaction, some potentially density-dependent noise, and some dispersal in space. Now, in general, you will not be able to solve the general form of this model for everything, right? It's a bit complicated, but somehow everything on this cube, this is really a problem, is morally equivalent to some limit of this. And for instance, I tried to convince you yesterday that going from this one-way causality to these feedbacks is really a question of diagonal versus diagonal elements in your interaction matrix, right? Self-regulation. This is very self-regulated. This is very low self-regulation, or nothing is acting effectively like a self-regulation. in a model. So, okay, now that this is said, you should, at the end of the lecture, I'll try to say that this does not mean that this is the standard model of ecology in the same way that we have the standard model of particle physics, right? The standard model of particle physics happens to be right. I mean, to some reasonable extent. This is probably not right as a model, but it still allows you to ask most of the right questions, I would say. That's at least how I use it. Okay, so I think from now I'm going to switch back to the continuation of the other lecture. So sorry for the jumps back and forth. The previous lecture was about networks, if you recall. And I ended up saying that at the end of the day for networks, where did I want to say that? Yeah, okay. Just basically, at the end of the day for networks, trying to predict the dynamics, the dynamical outcomes and the coexistence of species from network structures so far is a kind of not working that well endeavor in ecology, except in some cases. In some cases, maybe you can get something out of that, but that's not what you do most easily with networks in ecology. So one option is to say, I renounce understanding network structures in detail, and I will just replace them by randomness. That's not the only option. You could say, instead, I will assume that all interactions are the same, and I'm just going to care about what stochasticity would do, and then we're back to the neutral game, to the neutral theory type of things. So kind of, we could branch out in those two directions. Either I'm going to say interactions, I simplify them to the extreme, and I end up with neutral theory where it's everything else that is interesting, like space and stochasticity. Or I'm going to still get a tiny bit of complexity in interactions, which is the tiny bit of complexity that you get by assuming that they're random. So they're not identical. The interactions are what matters, what makes species different, but in the smallest way possible. And now you're like, okay, I heard about this from Stefano, at least for a while, and so I understand everything there is to say about random interactions. I think there are a few complementary insights I can try to give to help like flesh out this picture. And depending on time and depending on whether you feel like it, maybe I'll actually write one calculation on a whiteboard for the sake of people who like calculations. So the idea of disorder is just, okay, when you cannot understand something, whether it's the environment, you replace it by a random environment, it's a network, you replace it by a random network, and you get on with your life. I want to say, okay, we go back to Volterra, we say that those numbers are random. Okay, why not? Why could this be a good idea? I want to give you a few justifications that maybe you have heard or maybe not. And they're not the same justification for why there's different context or different ways that you could end up deciding this. The most obvious thing is just, okay, we have a hammer, we have statistical physics of disordered systems, so we know how to solve systems that have random interactions. We have a lot of tools for that, so it's going to be fun, for some definition of fun. Weird, like nerdy definition of fun, but to each their own. Another justification could be, I believe that how to say, I am interested in networks that have some structure, let's say food webs, but I don't know if that structure is really important for the outcomes that I'm looking at. Is the structure of the food web really important for, let's say, the abundance distribution? One thing I can do that's obvious is I just randomize the network, and if I get the same abundance distribution as before, then probably the structure is not that important for that outcome. At least it's not proven that the structure is really, you could have unstructured things that would give the same outcome, right? If you get something different from randomizing, maybe the structure was important, or maybe you did your randomization wrong, right? It's not trivial to know what is the right way to randomize a network to keep the right things constant so that you're doing a fair comparison. Yes? So that's exactly the thing. So let's say, you see, you have ecologists doing a lot of very hard work to measure interactions between plants and pollinators. And they realize that this network has, let's say, nestedness or modularity. Now you want to say, is this nestedness or modularity, is it just maybe a spandrel of evolution, an accidental consequence of evolution? Or is it something that really changes the dynamics of the system, that really has consequences on my ecological dynamics, my coexistence, my stability, all these properties that we have talked about so much? And it's not obvious that this structure should have any interesting consequence. Maybe it's just there and it does nothing, right? So one way of trying to see if it does nothing is, let's say I care about species abundance distributions. That's what I want to predict. It's a choice. Maybe for that prediction, the structure was not important in the sense that if you randomize, if you lose that structure, you get the same prediction. And maybe that prediction could be just a consequence of, let's say, the number of nodes or the number of links per node or something like this, right? Not really the structure of the network. That's very possible. So that's a game that ecologists play very often if they want to understand if whatever they have found is really the right mechanism or the right explanation for some outcome, for some phenomenon in nature, such as stability or coexistence or abundance, whatever. A third justification is that maybe interactions are really kind of random. So I'm saying that, in fact, here I was just saying I'm using randomness as a null model when I think that the truth is not random, but just to know if the truth is important. Maybe the truth is a bit random-like. And one way that you would get this is, imagine that all the interactions depend on a single trait. Let's say just the larger species or the most efficient consumer kills everybody else. Then if you look at an interaction matrix, an AIJ, typically it will have a very clear structure in it. Let's say the first species will kill everybody, the second species will kill everybody but the first, and so on and so forth. You'll really get a structured matrix here. Whereas imagine that for every pair of species, it's a different set of traits that are important for how they interact. Maybe species 1 and 8 are competing mostly over light. Species 4 and 6 are competing mostly through herbivores. Then there is no reason for these interactions to be correlated. And basically, random means independence. Every one of these things could have a very deterministic explanation, but as long as they're reasonably independent from each other, then the end result would be like a random model. So random doesn't mean unknowable. It doesn't mean strange. It doesn't mean changing all the time. It just means that those numbers are going to be sufficiently independent from each other. That's something that, like the central limit theorem, ends up working. Feel free to interrupt if that's not clear. And now the most ecological justification I want to give you is, yes, please. Yeah, well, if you had a purely multiplicative effect, let's say, then it would be log normal instead of normal, right? Because you can always say that the multiplication of many things is the sum of the logs, right? If you start to have something more complicated, then okay, we start to get into the weeds of, let's say, if you have the minimum of many things, maybe it's a bit more tricky. But yes, please.
Maybe you want to get to this eventually, but this kind of randomness works at the level of observables or what now you're the leading system. Obviously, what is the way in which you talk about it matters. Right?
Yes, absolutely. So I would say, at the end of the day, considering this, treating this as random or not, depends on what you want to predict or what you want to do to the system. If what you really care about is how is species 8 going to be growing in 1 year, then probably you need the precise numbers here, right? So you need to do all the experiments and whatnot. If you care about the abundance distribution of the whole system, maybe you don't care about that. So there is no absolute answer that you should do one or the other. It really depends on what you're trying to do to the system. That's a very good point. And actually, that kind of ties into my fourth point. So, you know, many ecologists feel that biodiversity is important somehow, that we have to care about biodiversity, that it's good, that it's cool. But it's not obvious at all that diversity in itself is a causal factor of anything. It's easy to say that diversity could be a consequence of things, right? Maybe diversity is increased by having more diverse resources. Maybe diversity is decreased by putting perturbations in the system or increased. But when is diversity going to be a cause of some other property of the system? When, for instance, is diversity going to be good or bad in some way for the system? That's not obvious at all. One thing that's really nice about random models is, in a sense, they're models. So, okay, before I say that, in a complex network, you know, if you have a very complex network, like I talked about yesterday, as I mentioned, it's really hard to know which structural metrics are meaningful. Like, is nestedness meaningful? Is it going to be causal for anything? We don't know. In a random interaction model, we can really find a metric of diversity that truly is causal, that really predicts many properties of the system. So there's, in a sense, why did ecologists start to look at random matrices and these kind of things? Because it's the most basic model in which diversity is the cause of something, where you can ask, is diversity going to be good or bad for, let's say, stability, right? Which was the original, like, Robert May paper. So, okay, this is this is what I'm saying here, right? It's one way to produce scientific statements, like falsifiable statements, like that, such as biodiversity increases stability, let's say, which is not obvious in a structured network, because maybe in the structured network it's not the diversity that counts. Diversity just is an accidental, correlate of some structural property. In a random network, diversity is really what counts in some sense. Okay, so those were 4 stories. You can take the story that you want for why we might want to write a random interaction model. You believe them if you want, you don't believe them if you don't want. I'm not going to try to convert all of you into disordered systems physicists. God knows we have enough of those, especially in Italy. Sorry, that was completely gratuitous. But okay. In my experience, I have not succeeded in converting ecologists into disordered systems physicists, so maybe I should not worry about that. Anyway, if you say that you're going to play with this game, and maybe you're going to play analytically, or maybe you're going to play in simulations. If you're not a physicist, typically it would be simulations, but it's fine, whatever you want. Okay, what do you get out of this? If you want to do the physicist game of trying to analyze this model, I'm going to claim, to make a strong claim, that's a bit of a surprising claim, that's, okay, if you have a large number of equations here, you have S equations, where S is the number of species. You have S square numbers here, actually S times S minus 1, because I have put 1 on the diagonal for convenience. It turns out that if dij are random, you can go as rigorously as a physicist ever is rigorous, from a system of S equations to a single equation, single species SDE, for if I was picking one species at random in the system and I was tracking it, what would its time series look like? And it's a logistic equation with some noise. Actually, it's in the case of that Jacopo was talking about, of a growth rate that would fluctuate in time, because the growth rate is here 1 plus psi, fluctuating in time. So a fluctuating environment, plus a memory term, a delay term, right? So this is a case in which we have a rigorous way to go from whichever model we want to really a single species logistic equation with noise and delay, right? That was my claim from the other day, that somehow all the phenomenology that we could care about in this model is somehow captured by a single species logistic equation with stochasticity and delay, with just one very important detail, which is that the amount of noise here, the amount of stochasticity here, actually, what do they mean, this stochasticity and this memory? The stochasticity here means if the other species are fluctuating, then it's like they're changing my environment, right? So it's stochasticity that's coming from the other species dynamics. And the memory here is the memory of how I impact myself by impacting other species, and then it comes back to me over time. So in fact, both of these terms are actually coming from the other species. This term here is coming from how the other species are impacting me like an environment. And this term here is kind of coming from how the other species are impacting me as a feedback, right? So this is why, again, I was telling you this whole story of how do the species enter into the R and into the A, kind of. This is a way for the rest of the species to enter into the R, kind of. And this is a bit the way that the other species contribute to the A. Yes?
But the C is deterministic, it's not.
Absolutely.
So how to think about it? Because obviously if I did something in the past, how I impacted myself through other species depends on.
And that's the extreme beauty of this thing that weirdly doesn't, and I'm going to explain why. That's extremely surprising, and I'm very happy that you point this out, because indeed it is extremely surprising. And it's the only reason why this whole thing works. In principle, you could potentially always write an equation like this, but it would have like terms here that depend on your identity, and that depend on the identity of everybody else. The fact that it boils down to a single thing here is the magic of the whole thing.
Earlier, there were pathways having higher powers of A and smaller powers of A. So higher powers of A eventually take longer time to affect. So
Yes.
Is that included in the?
Absolutely. So the effect that you have when T is almost equal to T prime comes from the very short pathways. and the thing that from T is very far from T prime come from the very long pathways, right? Exactly. So, okay, that's exactly what I was saying here. Sorry, I should have that while I was talking. Okay, am I going to do this? Not in detail, because if I want to do the whole dynamics, it's a bit hairy, as one says. I think I'm going to give you I'm going to give you a hint of how it works just in the equilibrium case. If I'm going to a single fixed point, then I can forget about dynamics. It's a nice thing that suddenly I don't have this T and T prime complicated memory, whatnot. I'm just going to a fixed point. And I'm going to give you the simple story. And if you really want, I'm going to give you the slightly more complicated story, and we'll see about it. So the very simple story would be to say, okay, how do I go from here to here? If I'm at a fixed point, what does it mean? At a fixed point, at a fixed point, instead of having these dynamical equations, now I just have the thing that is in the parenthesis is going to be equal to 0, right? So the claim would be that, in fact, at the fixed point, you would have many equations like this set to 0, and it would turn out that there's a kind of single equation like this set to 0 for my effective species. What are the equations? So for every species that survives, I'm only going to look at survivors for now, for simplicity. For every species that survives, it has this relationship, right? It's going to, sorry, I switched from big A to small a. For no reason, it's the same a. So every species is going to have this relation. I could tell myself, if I just picked one species at random, I could roughly write what happens to the moments of this thing, right? What would be the average of this quantity? Well, I would take average on the left and average on the right, and it feels like I should be able to say something like, you know what, average of n is going to be average of 1 times average of this sum, and what is this sum? The average of this sum is going to be roughly s times average of a times average of n. That would actually work if a and n were uncorrelated, right? Now, they don't have a real reason to be uncorrelated, because in fact, the n at equilibrium, they all depend on the A, right? They depend on the interactions. But if by magic they were uncorrelated, I would be able to just do this. The average of the abundance would be just something like this. The variance would be something like this. And then it's a system of two equations which I can solve.
I lost you. What are you averaging over?
Sorry. Averaging over species. This is at a fixed point, right? Everybody is at equilibrium now. So I'm just saying what is the average species abundance and which is the variance between species of abundances, right?
Averaging over S species.
Over S species, exactly.
And why this consideration 1 minus a again?
So this is just saying that if I take this equation and I average on the left-hand side and I average the right-hand side.
No, I maybe just go back this 1 minus the words.
It's just from here. Yeah, if I set this to 0, then I say that this is equal to that.
Yeah, now I understand.
Sorry, thanks. Is that clear for roughly everybody else? Yeah, take that question.
So in considering the average, do you have to assume that the ends are independent?
No, actually, the only thing that you need to assume is that the A, to write this, you only need to assume that the A's are independent of the N. Otherwise, it would be just average of A, N. Because, yeah, you would probably need to say, actually to write this properly, you would need to say that the distribution of A, ij is independent of I, right? That's because you have the same average of A for every species, right? So this is just saying there is no row correlation in your matrix, right? Aij is independent, A1j is independent of A2j. They're all drawn from the same distribution, right? If I wanted, yeah.
Does this mean each species interacts with every other identical?
No, actually,
the distribution is identical.
The distributions are identical. By the way, there could be many zeros in there. As long as it's not completely sparse, as long as there are sufficiently many interactions, we're not going to care. But yeah, everybody could have their own set of species that interact with various numbers. But just what a random network means at this level of the story is just that every species has the same distribution of interactions. Which means in the sense that no species is that special. They're going to be different, right? Some are going to be more abundant than others. Some are going to win a bit more than others, but it's only winning by chance. It's not winning because I'm really, because I'm a top predator, or because like a top predator would not have the same distribution of interactions than the plants, right? Because they would be interacting with different sets of species in a very directed way. I mean, Anyway, something like that.
Walk through why in equation 6 you get variance times n squared.
Because I have, let me remember how this thing works. Because in general, you would have the symmetrical thing of variance of A times n square plus variance of n times A square, or something like this.
Yeah.
And I think here I just did I think this is correct if the, let me remember. Sorry, I have a, yeah, I don't remember the explanation. I'm sorry. I'm starting to wonder, is this true only when the average A is 0? I'm not sure.
But it will not even work because it will be average A square, which is always, you know, the second term will be average A square.
But I think it works out. No, yeah, I think it works out because if you do the game, so if you do average of n square in this thing, you're going to have all the terms. But then if you go to variance of n, somehow you remove terms. Sorry, no, I don't know. The answer is I don't know, so I'm not going to say something wrong. The point that is nice about this thing is, so this is a system of two equations that you can solve that tells you what is the histogram of abundances, right? It's going to be a Gaussian with a certain mean and a certain variance. And you just need to solve this system for what the average is going to be. So that's very easy. The average is going to be 1/1 plus S average A. So the more you interact, the smaller the average, right? And then the variance is a bit more complicated to compute, but it's still easy. Yes?
Sorry. Yeah, maybe I'm missing something here, but then you're saying it'll become a Gaussian because of the law of large numbers, that it's...
Yeah, so for now, actually, I have not proven, I've just done the mean and the variance.
Right.
And so I'm not actually proving that this is a Gaussian.
Right.
Okay. In fact, this calculation is wrong in many ways. I'm going to go to a more right one that actually tells you why this is a Gaussian.
All right.
Okay.
No, I'm just wondering because for it to be a Gaussian, you would again want the ni's to be independent of each other, which in at least the limiting case, n-1 can only be independent. All n cannot be independent.
So the thing that's important is the thing that will make the whole calculation work is that even if the n's are not independent of each other, as long as the a's are independent of each other, then an is independent of an. I mean, any an is going to be independent of any other an.
Sure.
So that's the thing that's going to save you. Anyway, that's actually my next slide, I think. My next two slides, sorry. So, okay, why would it ever work to be able to just say this, to say that, in fact, any species is going to be like a randomly drawn abundance with this mean and this variance. So it's saying that I can go from a network to just this kind of, distribution where there is no special role, no special position. Any species at random is kind of seeing a fair sample of the whole community, right? There's no bias in how a species is seeing the rest of the community. So the game is definitely about the central limit theorem. What the central limit theorem tells you, the strong version of it, or the, I don't know if it's strong in a mathematical sense, but the broader version of it is even if each of those variables had a different distribution, as long as they're independent, then the sum of it eventually will converge to a Gaussian where the mean is the sum of the means and the variance is the sum of the variances. So this is very strong because I don't even care that they're identically distributed, in fact. I don't even need to care that much. I just need to care that they're independent from each other. So I guess the whole mathematical game is, in principle, all these numbers in the sum are not independent from each other because again, the abundances are not independent of the interactions. And they're not independent of the interactions with other species either, because this is all the result of interactions, right? So the game is the magic of the cavity methods that I can talk about it. I can talk about it from now for, let's say, I have time to do this. So the trick that physicists ended up using, I'm not going to go too deep into the trick, but I'm going to go deep enough to give you an idea. So the trick is to say, look, I know that at equilibrium, I have this relationship here. I'm going to use really this notations, this specific parameterization where R equals 1 and A11 equals 1. Okay, I have this problem that I cannot go back to this simple explanation because these terms are not independent of each other. Thank you. Now, one thing that's one way to get to independence is to say, imagine that I have a community with many species. I going from 1 to S. And now imagine that I add a species 0 to the system. Now what's going to happen is that if I write the equation for this species 0, so it's just going to see 1 minus n0 minus sum over I greater than 0, a0 I and I. Nothing new for now. The point is the initial growth rate of this species 0, it's invasion fitness. So at t equals 0, if n0 is almost 0, then what you have is well, very small compared to 1, let's say. Let's say it goes to 0. It's maybe the saner way to write it. It's going to be approximately 1 minus sum over I larger than 0, a0i, times the equilibrium here. I'm going to write, I think that's a bit annoying, but please follow me. This n star I slash 0 is going to be the equilibrium before species 0 arrived into the world, right? It's how the system was before the invader came. And now the thing that's very important, and that's where that's the first step of the whole magic, is that now these terms are independent. There is no reason for the interaction of species 0 with I to have anything to do with the abundances of I before 0 was in the world, right? Before 0 arrived, species had whatever abundances they had, and it doesn't relate in any way to the interactions of 0 with anyone. So in fact, here you can really use the central limit theorem for sure. There is no doubt here. Your invasion growth rate is pure, sane, rigorous central limit theorem. So I know that this is going to be a Gaussian. As long as there are many terms here, it's going to be a Gaussian with the mean that is what you want and the variance that is what you want. And now, what is the second step of the magic? So the first step of the magic is invasion rates or fitness, invasion fitness. So the thing I had called R tilde, in my previous lecture, R tilde 0 happens to be well controlled, no problem in this model. Now, assuming that you have drawn a species that coexists, what's going to be the story? Well, assuming that they still coexist at the end, that 0 coexists with everybody, you're going to have the same story as every time, which is going to be something like it will start from some R tilde 0, and it will go to some final abundance n0 star with some slope. And now, what is the slope? Well, the slope is just going to be given by, it's a bit more annoying once you have two species. But so basically, so this is the second part of the story. It is, what are the feedbacks for the invader? So I will write them this way: dn0 star over dr0. And okay, in the case, so if 0 coexists with everyone, with all I, then it's just the inverse matrix, right, of, as usual. You're just going to have that n0 star is going to be sum over I of the inverse matrix, so A minus 1, 0, I applied to Ri. Okay. So if I do this derivative here, if I want to have the feedback, so remember that if this is the slope, then A00, so 1 over A00 is the feedback, is the susceptibility here, susceptibility matrix. Okay, so the question is, how do I compute this thing? In principle, it could be very complicated. Now, what's the magic of it is, when you have, if you assume that, oh, sorry, it's a, yeah, let's say small a. I'm sorry, I keep switching between big A and small a. I really apologize for that. Oh, shoot, I skipped one step. Sorry. Okay. Pause. If I just go to this story here, there's one thing that you'll notice immediately, which is that if the average interaction here was, let's say, 1, you would have that the interaction term is super large because it's when s goes to infinity, it becomes infinite, right? So as you may have seen with Stefano last week, and as you may recall, the only way to have that those numbers are going to be of order 1 is if the average of A is like 1 over S, and the variance of A is like 1 over S, right? So for those things to remain sane numbers, if I want many species to be able to coexist, I need their interactions to be on average and invariance kind of small, right? This is important for the last step. Why? Because it turns out that if Aij is distributed like as whatever you want, so has that Aij average is like 1 over S, let's say mu over S, and variance of Aij is equal to sigma square over S, let's say. So that's just mu and sigma are just parameters. That shall I just say that mu and sigma are of order 1. They could be 0.1, they could be 10, they could be maybe 50, but they're reasonable numbers. So if Aij has this, then in the limits S goes to infinity, then A minus 1 tends to some constants V times the identity matrix plus something order 1 over square root of S. And that's something that's magical. So that's where the magic is happening. It's a property of random matrices. So if the Aij are random numbers in this scaling, when you take the inverse matrix, it's a diagonal matrix with this. So everybody has the exact same feedback in the community. So in fact, instead of having something complicated here that I don't know, it's going to be very simple. N0 star is just going to be wait, am I doing the right thing? Wait, let me think for a second. No, this is not, wait, is this true? Yeah, this part is true.
But for the random matrix, we have to fix the diagonal values to get this.
Sorry. You're absolutely right. I really apologize. This is my fault for taking out the diagonal. I really appreciate that you're following this and not allowing me to be insane or wrong, at least. Okay. Wait, I wonder if I made it. So this is why I should never use the whiteboard. Did I make a mistake? I think what I'm writing is correct. Oh yes. Yeah. So the point is, okay. I'll do the block inverse. To do it properly, I need to do the block inverse. Yes. Okay. So what I need to do is, in fact, I apologize about that. What I want to say is, N0 star is going to be the N0 star dr0 times r tilde 0. The way that you get there, yes, sorry, oh no. Okay, the way that you would get there is this. Okay, this is an aside for people who care about the math. It's not going to change really the meaning. Maybe I'll take just 1 second to dwell on this before I go to the right way of doing the calculation. And I apologize for the confusion. So what this thing is saying is deep down precisely the answer to the question that Sergey was asking before, which is why do all species have the same C? Why is there a single memory term? in fact, it's a property of random matrices that somehow the inverse of random matrix in this scaling is a very self-averaging property. It's a very robust property. It goes to a single number instead of being something that is fluctuating. So if you take many different random matrices, they will have the same exact number on the diagonal as long as they have the same statistics here. Okay, the inverse will have the exact same number. What's the right way to do this? And I apologize for the, I mean, at the end of the, yeah. I don't know, I'm really hesitant to go into the calculation, but let's do this. Let's do it, okay. What I want to say is this. N0 star, so that's the linear algebra way of doing it, which is not what you will find in most papers on this so-called cavity method, but it works. Ri, this is the sum of 0i. It turns out that if you have a matrix here, which you construct like this, so there's species 0, and then there is everybody without 0. The inverse of this matrix, you can do a block inverse. It turns out that this thing here is going to be, so if I call this matrix V, turns out that V00 is going to be 1 over A00 plus sum over I, A0I, A without I inverse, A J0, sorry, sum over AJ, and V0I is going to be V00 times A0I. And so if you actually, you can just do it, and it's a known thing, which means that if I get back to this thing here, this is how I'm going to prove the expression that I wrote here. It's that if I start from N0 star is equal to sum over I, V0I, Ri, I can also say it's V00 times R0, which is 1, plus sum over I, A0I, yes, times the abundances. Shoot, no, it's this times the inverse matrix. Yes. Shouldn't be that hard, I apologize. It's going to be sum over these things here, J times inverse sum over J, Ji. So this is block inverse. It's a well-known formula. And this is going to be sum over A0I times the inverse without I applied to, so inverse without 0, sorry, what I've been doing, inverse without 0. Sorry about this. Inverse without 0 applied to R, and this thing here is R0 plus some A0I times N star I without 0. And so we're back to, this is equal to V00 times the R tilde 0 that I computed before. Does that make sense? Or did I lose everybody completely? That's for people who care about the derivation. You will note that this derivation tells me, okay, what I said before is R tilde 0 is given by the central limit theorem, right? Here, this is R tilde 0. So I know what it is. And V00 is going to be the same V for everybody. So I can drop the V. And all that is tells me is, at the end of the day, for everyone, for like species 0, its final abundance is going to be some number times its initial growth rate, and the number is the same for everybody. So if it's true for 0, it's also true for all the I. And so there's no reason to treat species 0 as special in any respect. We're going to have the exact same statistics. So what changes compared to the equation I had written before is very simply that if I go to the equilibrium, finally, I'm going to have, so N0 star is equal to V, some V that I can compute, times R0 is 1 for everybody, and R is 1 for everybody here in this, and those were minuses probably, because of my choice of signs, and those are small a's. Sorry, I'm being a bit of a disaster in here. V times 1 minus sum over all I, A0I, N star I without 0. So this equation here, now, this is what replaces these equations here. Instead of it being true, that I can just take, so these equations are correct, but those numbers are correlated. This equation is still correct for everybody, but these numbers are now uncorrelated, right? So I can just take the average to the left and to the right, and there's no reason for species 0 to be special. And so you just get at the end, that's the whole game that we've played, this whole very complicated thing just gave us the number V. Like it just changes all these equations by a factor of V. Yes.
So previously we discussed that, okay, if the self-limitation is there,
Yes.
it will change from feedback to like environment. So the scaling we are taking, let's say there is large number of species, the diagonal terms are not changing, but the cross interactions are decreasing with S. That's why like we can write this from like in a, like all other species become some sort of environment for me.
Yeah.
That's why I can write this.
Absolutely. That's exactly the point. All species just become like an environment somehow. If you didn't know, like if you just look at one species alone, the species in a sense has no idea that it is in a community. It feels like an environment. The only thing that it gains from the other species is somehow this V could be different from one. In fact, it turns out that this V is a function of the symmetry of Aij and Aji. So if Aij and Aji, if Aij, Aji is equal to A square, if they're not correlated, then in fact this V is equal to 1. So in a completely random matrix, in fact, I have no idea from a feedback point of view that I'm with other species. I don't see them at all. They just act like a random environment on me. And so that's exactly the point I wanted to make. So thanks a lot, which is, I think I talk about it at the end, sorry. But it's really this point that somehow in this scaling, when I choose interactions to have this scaling here, which is a scaling used by Stefano and by everybody since Robert May, in that scaling, other species are effectively like an environment. They do not matter very much for your feedback, or if they matter, it's just in a constant way for everybody. So a species doesn't really know. Yes.
Sorry, quick question. Intuitive, I might have missed this, but intuitively, what does V represent here?
V is, sorry, it's the dn star over dr. So it's how much, if I were to change my growth rate, if the environment becomes more favorable or less favorable, how much in the long run is going to impact my equilibrium abundance, right?
Right. So basically, you're adding a strength of average interaction, how it's modulated by feedback.
So yeah, so it's something that tells me just effectively how much am I making the world worse for myself when I'm growing. That's the slope of this thing. If the slope is very sharp, then even with a large growth rate, I will not go to high abundance. If the slope is very shallow, then even with a small growth rate, I could go to high abundance because I'm making the world not so bad for myself.
What would be the value of V for two important cases where Aij and Agi anti-correlated and positively correlated?
Right. So if AIJ is positively correlated with AJI, so if you go to a more symmetric case, then V is going to be less than 1. No, sorry, more than one, because by killing your competitor or by helping your mutualist, you're making the world better for yourself. So you overshoot a little bit what you would predict if there were no interactors. If AIJ is anti-correlated with AJI, let's say predator-prey or asymmetric competition, then as I grow, I make the world worse for myself. Right? I deplete my prey, and so V is less than 1. Thank you. I can actually write this. That's a very good. So let's say this is, I'm going to write.
It is simply 1 plus correlation coefficient.
Not exactly. It's a bit more tricky than that. Equals 0. More than 0, V is less than 1, and less than 0, V is more than 1.
And where exactly is it? Again, I like anybody else, I lost you in this calculation. Where exactly was calculated somewhere?
So in fact, here I did not tell you what the V is. You can actually show that there is an equation on V that is quite simple.
So this is comes when you try to, you have identity matrix plus matrix with all matrix element being small, but the sum of the matrix elements in a row comparable to 1.
Yeah. So I didn't. Yeah, exactly.
Take inverse, and you're getting something like V times identity matrix. And that was magic, linear algebra magic, where all of the things were coming out.
Yeah, and I can show you actually there is a simple equation on V, which if I remember correctly, on the small v, it's going to be, just from memory, v equals 1 over 1 plus correlation Aij, Aj times fraction of surviving species times v, or something like this, where this is a probability that n is larger than 0. So you just solve this thing, and you get v. Yes, v is in both sides, so you solve it, and then it's a bit of a complicated expression. Don't quote me on this. Just go look at the paper. But yes.
Once again, when you're taking this inverse, right? I plus something small, but not small in terms of sum.
Yeah.
Is there another intuitive way of understanding why there is, or it's, I just have to take the trust?
So I'll talk, maybe let me come back to this a bit later. Okay.
And
yes.
Pies in the numerator, everything else is.
Ah, yeah.
So 1.
Oh, minus. Thank you. Okay, and okay. So I'm going to write it explicitly, so that I don't introduce any other notation. And the way that you get this is just through this self-consistent equation. If you ask yourself, now you have a self-consistent equation that has V in it, and now if from it you ask, okay, what is going to be the dn over dr in general, you get an equation that has V on both sides, and somehow it works out. Yeah.
So the numerator is this field that larger than 0 is something which you can calculate if you know the Gaussian distribution of n's, and just calculate them.
I think the only thing that's missing here is when you're doing the sum and some species go extinct, then instead of just s, you get a pi times.
Exactly. So that's the point that is non-trivial here, right? For this whole game to work and to give you the right solution, I did three things. One is rigorous. It's the CLT here. Another one is rigorous. It's the inverse of a random matrix. That's an algebraic property. It's math. The thing that is not rigorous is I computed n as if 0 was coexisting with everybody. I didn't care about extinctions, creating non-linearities. And in fact, I get the right results with the slight detail that I should actually care just about the fraction of terms here that are zero, that is just going to tell me which species are extinct. It's not obvious at all that extinctions can be taken care of just by asking how often is this number going to be less than zero, and I just remove that from the calculation. It turns out that it works, but that's where really the non-triviality and the mathematical weird underpinnings of the cavity methods are. Everything else is safe. It's linear algebra, it's safe, and CLT. So yeah, if you want to care, yeah.
Is it the cavity only works for Lotka-Volterra or for, say, consumer resource in which you have the exponentially amplified resources?
Sure. You have an infinite cottage industry of people applying the cavity method to everything that you could imagine. So you can do it for consumer resource, you can do it for neural networks, you can do it for whichever thing you care about. And there are some limits, some notions, like some handle on when it's actually going to fail bad. So yeah, maybe you want to say something? But yeah, typically anything that looks like this regime I'm mentioning here has the right properties for it to work. Yeah. Yeah, I'm sorry. Sure. So the argument is, once again, is this. And thank you for giving me the opportunity to go one final time, just slowly, cleanly, without all the jiggling around, which tells me I should really have prepared this better. So if I have an equilibrium relation, so at equilibrium, this relation is just given by Lotka-Volterra. This is true by the definition of the model. Assuming here, of course, that everybody of this, I mean, yes, this is true. Well, this is true. Now, what I say is, this is true, but I cannot solve it even if the Aij are independent numbers between themselves, because they're not independent from Nj. So I cannot apply the CLT to this. The trick to apply the CLT and to get somehow like random numbers is to say, if I don't look at the species altogether, but I just add one species to the system, then now the place where I can apply the CLT is not on its final abundance, it's on its initial growth rate. Its initial growth rate is this expression here, which is a sum of independent random numbers. This is independent from that because the abundances before the invasion are not in any way linked to the interactions with the invader.
So that's assuming that there's a new species.
Yes, exactly. I'm adding a new species which didn't exist. So for the initial growth rate of this new species, this is a random variable that obeys the central limit theorem. So that's no problem. Now, the whole game is, how do I go from the initial growth rate to the final equilibrium abundance, right? If I could do that always, I would always be able to somehow, for any model, I would always be able to say, I have the CLT here for this initial thing. From there, I infer the final N0. Now, the thing that turns out is the slope here is something that is in fact very easy to compute if you're in a random matrix. And not only is it easy to compute, but actually it's going to be the same for everybody. Under this assumption, so when is it just a line? It's a line when all species coexist.
Can I just briefly interrupt so that I'm not lost here? So I understand the argument about R0 when it's very small. Is it all I need to calculate this P of n larger than 0 in the numerator? Actually, so because obviously it's invadability question. So as soon as it can grow a little bit when it's very tiny, it can then grow to some. So this P of n larger than 0 is trivial to calculate. It doesn't involve V at all.
Absolutely.
And then if this is a number which I can calculate easily, then this whole equation for V, which is written in the upper right corner, is just a quadratic equation.
Yeah. Okay. Quadratic why? Sorry?
Because if I multiply V's in the numerator and denominator, so if I multiply by both, it will be a quadratic equation for me.
Exactly. And this is why I didn't write the solution, because I don't want to write square roots and whatnot, but it's really just a quadratic equation. Now, it's not obvious at all that just like the probability that R till 0 is larger than 0 should give you automatically the number of survivors. Why? Because adding that species could kill many others, right? It turns out that this equilibrium calculation is correct precisely in the regime to have a fixed point for this process to have a unique fixed point. It's precisely the regime where when I invade, if I'm able to invade, typically I will cause a small fraction of less than one extinction. So I don't need, somehow I can find a fixed point of this system. If every time I invade, I create one extinction, then suddenly someone else could invade again, and I get in fact into not a fixed point, and that's what I'm going to talk about next.
Yeah. No, I interrupted when you.
Yeah. Right. Sorry. So the only thing I need to care about is what is the slope of this thing. So one way to think about it is as this A tilde. Another way to think about the same slope is its inverse, which is just how the.
You know, that line matters for purely logistic growth. But
Yes.
when you have interactions, you know, that's not the only thing that contributes to the fixed point value of the new species.
It is. So this is not the A00 when you're alone. This is an effective A tilde, which is in fact which involves your interactions with everybody. The point that is maybe surprising, but so in Lotka Volterra, as long as no one is going extinct, the equilibrium condition is purely linear. So in fact, the only thing that interactions can do is change the slope of the line that goes from R0 tilde to the equilibrium. There cannot be anything but a line here. I mean, what I mean is you can compute the effective. If you want, one way to think about it, the way I proposed to think about it yesterday was, imagine that all the other species are going very, very fast in their dynamics. That should not change the equilibrium point, right? The time scale should not change the equilibrium. If they're all going very fast, then all the Ni are a function of N0, and they're a linear function. So if I replace all the Ni by their value as a function of N0, this is the coefficient I get.
Okay, so this is some effective one.
It is an effective line, indeed.
Okay.
It is the exact line that you would get if all other species had infinitely slow dynamics compared to infinitely fast dynamics compared to the invader. But even if it's not true, then the starting point and the end point of the line are still true, are still the same. Because the equilibrium cannot depend, neither the invasion growth rate nor the equilibrium abundance depend on the relative timescales of the dynamics. Right.
Okay, so okay,
yeah.
Please carry on then.
Right. So the only thing I need to find is what is this effective slope, which I can also write as this. This is what I call capital V00 also. So I have several notations for this thing, and maybe that's also what is not helpful. This is this capital V00.
It's the derivative with respect to what?
It's the derivative of your equilibrium abundance with respect to your growth rate, right? To your bare growth rate, to how you grow alone. That's yeah. I don't know how helpful this derivation was in retrospect. The point is, effectively, as long as all species coexist, I'm going to be able to compute this line. It turns out that this line in a random matrix is the same for everybody, and that's the core of what the cavity is saying. That
everybody means that you have just one species which is coming in, right?
Yeah, but it turns out that if you were doing it for any other species, if now you leave 0 in the system and you remove 53, and you let 53 reinvade, 53 would have a different R tilde, but it would have the exact same slope. And that's a property of random matrices in that scaling. It's the very non-trivial thing that each element of the random matrix fluctuates from one species to the other, from one realization to the other. But elements of the susceptibility here is a strongly self-averaging property of a random matrix, and therefore it does not fluctuate between realizations of the random matrix. I mean, it fluctuates with order 1 over square root of S.
Maybe I'm really leading us down a deep rabbit hole, but you know, I always interpreted this decision of random matrix people to make the diagonal exactly -1, AI -1, as saying Well, one can always renormalize the units of the abundance so that it is true. That is correct.
Yeah.
But now, if I renormalize the units of the abundance of every species, it will also affect the values of A.
Sure.
So in some sense, many of your voodoo magic here relies on the fact that this diagonal is -1 and everything else is small.
Actually, no. The thing that's, I mean, it relies on everything else being small compared to the diagonal. That's always going to be true. But you could start with a matrix that has not ones on the diagonal, and you can still run the whole method.
Okay.
And what it's just going to say is that now suddenly this V00, instead of being the same for everybody, is going to be 1 over the diagonal times something that is.
Okay, that's good to know. So, yeah. And now now I have a much more shallow rabbit hole by saying that you are trying to say that you are solving it for the case where self-interaction is always factor S stronger than interactions with others.
Yeah, absolutely.
And if you now imagine like real life applications where you may say that competition with yourself will always be the strongest, but competition with somebody who is evolutionarily close to you may be only 10% different, not factor 100 different. So that's the limit of this whole.
Yeah, so that's my point 2.4. So okay. I'll go back to this. Thank you. So first of all, let's assume that you believe in the scaling. Like you don't have any reason to believe in the scaling. That's fair. Assume that somehow, for some reason, it is true. Then what can you predict from that? So the thing that's nice is you only need to know now something, this mu and sigma factors that I put here. And out of them, you will get abundance distributions, but you can get more than that. You can get many different patterns from it. So abundance distribution is the obvious thing that you get. And what you would guess from here is if you just put this model exactly like this, what you get is a truncated Gaussian. It's a Gaussian, except for the part that is below 0, which is just stuck to 0, because you cannot have less than 0 abundance, which is not very reasonable, but it's easy to make a variation of this model that will have something else than a Gaussian. So the fact that you get a Gaussian from this and that you don't get Gaussian abundances in the real world is not the killing factor for this model. It's a small change that would give you that. Now, you could also try to think, I'm going to go to other distributions. This is, let's say, a distribution in time of for how long do I see a species in the system and whatnot, or what is the correlation between the abundances of 2 species over space. Of course, in this equilibrium derivation, you could not ask about this. You have to be in a non-equilibrium situation. But you could, let's say, do the same equation with noise, and then you could ask these questions here. Why not?
How can you get anything but Gaussian from a central limit theorem?
So the point is, at the end of the day, if you have many additive interactions and many of them matter, then in the units in which, so this thing here is going to be Gaussian, right? But it's not true that necessarily this is going to be a linear function of that. This could be 1 over that, and then when that touches 0, then you go to infinity, right? This could be some exponential of that. Right? There's nothing preventing you from building a model in which, in fact, for instance, when you write a neural network model, you will have a sum of neurons, but then you will have a sigmoid function here, right? When Priyanka was talking about functional response, you would have maybe a saturating function of those things. So that's how you could get basically any abundance distribution you would want.
So that will require you to go beyond Log-Volterra, but that is fine.
Exactly.
Nobody really cares about.
One way to go to stay in Log-Volterra and for this to still work is if you say, this is only in units where AII equals 1, but maybe in the original units, AII was very widely distributed. And so in fact, it's the convolution of distribution of AIY, which could be log normal, which could be whatever you want, AII, sorry. So there are always ways that you can say, you know, my model with 2 parameters doesn't work it, but if I had this 3rd parameter, and I'm willing to get a B minus, but now I can get my abundance distribution right. Sorry, okay, maybe C. Right. So the point I wanted to make with this slide is you can use this theory, and I'm not going to prove it, to do things that look like this data. Why not? The problem is none of these things are really a smoking gun for random interactions, in the sense that you could get the same patterns as with a random environment and zero interactions, or a random environment and neutral interactions. All these things are going to give you, are able to give you those patterns. So those patterns are not ways to say, oh, it was really worth going through this horrible derivation I did, because that's the right model of the world. Now, one thing that is a bit of a better smoking gun, and that's the thing that is unique to this random Malgova compared to neutral theory.
So I already said that the philosophy, I will not repeat myself.
Like
increasing the competition makes all the bugs
when I say
worse off.
That the random network is a bit like a single
relaxing the competition makes all the bugs better.
What this means is that the whole community is effectively in a single coherent dynamical regime.
Let's look at another more complicated
doing one
system.
thing,
7 bugs, 7 resources. I will not bore you with the stable.
Either the whole community
I'll just say that in this case, n log n generate, well, actually, maybe it's not even close to n log n over e log n, but
a phase
the
diagram.
fact is that in this particular system of references, there are 5 stable states, S1, S2, S3, S5.
It's a neutral theory.
As I already told you, all of the states are, in some sense, hierarchical.
With random interactions, you can get
play this game
dynamical regimes where you could get
we could have started with this state, which is the best for all
slightly larger
the
regime
microbes,
where
right? The way this hierarchy
which actually
works is that
it's not even in that
state
scheme,
where bugs get the most desirable resources they can have in a stable state. That's where they have the worst.
And then if interactions have more variables,
and they are kind of imperfect,
then you go into a regime where you have chaos.
Graph,
you have permanent equations of the dynamics.
Remove specific nutrients.
There is no noise from the environment. There is no stochasticity. Those are purely deterministic equations.
But removing
just the fact that interactions are heterogeneous enough
for remaining nutrients.
Someone starts growing, starts killing someone else. Now someone else can start growing, kill someone else,
so you are
and you get permanent chaos.
You are
going around like this.
Living in
and
a
I'm
more
going to claim that basically
world, so you will end up with the worst
transitions is a much better
removing nutrient finds, which is here,
kind of models,
removing nutrient ones, which is
anything
here,
like
removing nutrient
abundance
3,
distribution
which
that
is here,
always cheats.
removing nutrient 1, which is here, and so on. So this is all the transitions which are triggered by, if you want breakups, you may say that I removed the nutrient and then reintroduced it. It's almost the same thing as we were playing this.
This is the world in which interactions are small because I want S times average to be order 1
disappeared
for
a while, and
then
to
be order 1.
started lowering
this
down
is the original
and then
word where I
one
could allow
wife
myself to go
reappeared,
to
and
interactions that are 90%,
happens.
Well, exactly what
On the
you
other hand, removing
interactions are 90% of my
self-competition. Removing microbes relaxes.
If you go to that world, this is a strong interaction where my interaction with others are comparable to my interaction with myself.
So the take-home message here,
in that world, I can still write this phase diagram.
I had one more slide, but
the problem is when the interactions with others are comparable to mine,
there are multiple states, and you can trigger, almost like in this game, you can control the transition between those states by either adding or removing either microbes or nutrients. And the general logic is that whatever increases competition will lead to a worse state, whatever increases competition leads to a better off state. But not all the removal trigger transitions. So here only nutrient 1, nutrient 5, and
this is the regime in which you get
if you are in state 4, lead to a transition.
Does the removing of a microbe and
multiple attractors, because I
saw result in a
my so here, in all cases, I remove and then I reintroduce.
So that's the fun thing.
So it's almost like
this region. If you go to small enough species numbers, what you see is not chaos. What you see is limit cycles.
Yeah, that's what I was going to say.
And then as you increase S, you have period doubling, transition type of thing to chaos.
Nutrients again, we didn't want to introduce extra ones, and multiple attractors will still be chaotic attractors for multiple stable.
Okay, so the mess is transiently as long as you're close enough here in simulations. Let's look at simulations.
Shift to this nutrient, we reintroduce it back, something like this. And here you remove the microbe by, say, knocking it out with antibiotics, but then eventually we reintroduce it through, colonization.
4 species surviving or 10. Sometimes you will have chaos, sometimes you will have multiple stable states, sometimes you will have multiple chaotic attractors, or 1 stable and 3 chaotic attractors.
N5 over there.
It starts to be crazy.
You let the game
craziness happens.
Eventually you reach a state where all but one species would have a nutrient, and at that point you imagine the nutrient comes back and it gets paired with this.
Stronger than self-interaction.
Then that's where the thing stops.
Then
so
you get into
in that sense the nutrient is
exclusion, and now you're back to
removed
stability, really
and then
stable state. You don't have this chaos anymore.
And it would be introduced again.
So I guess
in the unstable structure or
in the next few minutes, I'm just
this is sort of where the sort of game comes in.
Okay,
so
this
just to repeat the question was
that is nice
if
for
you were on the right where a really competitive microbe was removed and it was reintroduced, wouldn't it like to go back to things where it was?
What Stefano
and I think here the answer is no. For the purposes of this game, it goes to the thing that's available. And then as soon as it goes there, the game stops.
That's actually an interesting
point. Might be somewhat artificial, but
it's
this is the game after all.
The prediction here is
there's
a small region in terms of variance and correction.
I mean, I think
there's a small region in which everybody will survive together.
Then
there's a larger region in which
that's a very good question because in fact this whole
unique
kind
stable
of
fixed point that is not invisible. But not everybody
very sensitive
only
to
a fraction
this
of
ratio.
species survive.
So the moment one side exceeds the other in numbers, it very quickly results in a big relaxation of the competition. So again, if you have a slightly more resources than microbes, you will get a the world in which microbes will be
smoking gun? That's debatable, but at least it goes in the right
all
direction.
those alternative niches to occupy, and they will be able to pick close to their
was actually also part
and vice versa. If there are a little bit fewer resources than microbes,
did an
the
experiment
competition would be fierce. So and this is literally like
bacteria, and then you do repeated dilution and growth cycles, and then you sequence to see the time series of those communities. And the idea is that you have up to 48 species that you could put in your system.
I have a few more slides. I actually have one kind of,
very nice thing about the system
one slide I just wanted to give you
unique, let's say,
a flavor about how many states you end up with this random action, sort of this n log n,
which is not so common to get. Like here,
an idea of how about it. So if you have 10 microbes on average, you'll have 3 states. In fact, the way that they built up the 7 by 7 was unusually high.
When you go from low nutrients to high nutrients, then you increase the strength of competition. You go from
this is a histogram of the number of states. As I said, it has a fat tail, so you can,
good fraction
if you
of
are
species are being
really
excluded when you do pairwise experiments.
Twisted rankings,
you that
you
you're
get
getting
as many
into the
as
region
160 states, but on
several
average,
interactions are larger than one.
2019.
You really go from somewhere close to here,
for 200 by 200, you get 86 states. So again, n log n is
not just the transition between those feasible
function. So
and where everybody survives and the yellow were
this is a result just from pairwise experiments. I'm going to show you the results for many species experiments right after.
I think I have 15
so this
minutes,
is just
but I have a logical break in my talk, so I'll probably,
if I do a pairwise, this is the
after I tell you this biological story, I will probably wrap up and leave the CNN story for my next lecture.
Well, there is an orange square here, then the two species existed together.
Even though
because the numbers are roughly the interaction coefficients to measure by looking at how much it reduced the imbalances
of microbes and nutrients is not directly realizable.
It's hard
and
to say
the reason why it is not realizable is that
the mean and the variance of
the only way you can think about it is what happens in a chemostat. And in a chemostat, you really don't have the situation where you mix the active factor in the chemostat and they will use one
both the mean and the variance of interaction, so we're going roughly
that is why
from
we
around
thought
0
hard
towards
how to introduce it.
Region
and
of
we
maybe
didn't
chaos,
find
maybe
a real kind of direct experimental implementation of this model.
Well, in fact,
nevertheless, some of our conclusions were
what you get from simulations. It's the same diagram, but not in the same units.
More realistic model about which I will tell you
and variance
in a lecture or two.
On the y-axis, and I changed the number of species.
Things which we actually saw already in our little tutorial. Remember when we run exercise number 2, every man had a different top-choice woman, and that meant that the whole proposal game ended up on the first round. So everybody proposed to the top-choice candidate, she accepted, and that's the end of the story.
And when I say fluctuations,
if you want
this is
happier
in the experiments.
The happier
an example where you have
reasonably
stable equilibrium, and an example where you get
turned out that
big
this
fluctuations.
is still
Those are not
a true
very
story
long
when we realistically
here,
assemble microbial community of dioxin bugs
thing, and suddenly the yellow
not in a chemostat, but in serially diluted environments. What we found is that eventually the stable
there are different ways that you try to evaluate the stability and the feasibility and
different from each
to debate them.
So this part is correct.
Roughly speaking, those are results.
Now I wanted to give you a flavor about in our ISME paper we needed to connect the whole story.
I didn't do the experiments myself,
real life.
I don't know much about the underlying biology, but at least I think this is correct.
The studies by Eric Martin's lab from University of Michigan.
This is not for the same numbers, right? So it's not a quantitative prediction from here to here because we don't even know what the numbers should be on the y-axis.
6 or 7 of them,
but qualitatively,
more.
you have
all
this
of
thing
them
that if
are
you put,
of the genus
if you have one or two
Bacteroides,
species
and
together,
Bacteroides, many
they
of
do
you
not
know,
fluctuate,
they like
they reach a stable
polysaccharides. So
equilibrium.
Bacteroides inhabit our gut, and they are the guys who
together,
are
or
happy
24
when
or
we
48,
eat fiber. So
no,
your
no matter
doctor or
which
your
species you
wife
put
tells
there,
you
I
eat
mean,
more
it
fiber,
doesn't
eat
seem
more
to be,
fiber.
I mean,
You eat more
it's not
fiber,
about the
but what
identity
really,
of the species
who really
so much
gets happy are
so much as
Bacteroides,
it's not like there is
because
one species that will always
we cannot
fluctuate, and if you put
digest
it,
fiber,
then
and it
the whole
goes
community
through
fluctuates.
all the way down to our
No
lower
species
intestine,
fluctuates by itself,
and then
no pair
Bacteroides
fluctuates by
start
itself.
chomping
But
up
if you put enough
fiber,
species
you know,
together,
those polysaccharides into
starts
their
to fluctuate.
constituent parts, and then the constituent
Is this-
parts are
you
consumed
should
know it, both but by why Bacteroides and by
why
some
the
other
low
species,
nutrient
and the entire
conservation
trophic
is
cascade
low
of
interaction strengths, whereas high
metabolites in the
is
gut
high?
starts.
It's
So
not
it
obvious
turned
at all.
out that the Bacteroides are very picky about
probable
which
explanation that I
fibers they
got
like
from people who
best.
understand the
So
experience
here are
better
two closely
is
related
at low
organisms,
nutrients,
and
these
this
bacteria
lab figured
are
out their
growing slowly and
hierarchy.
activating few
So again, those
metabolic pathways.
CSP,
At higher
PGA, or
nutrient
whatever are
concentrations, they start
abbreviations of
to
some
do a lot of things, then they
unpronounceable
have they do lots of things that are
polysaccharides.
toxic for others.
But this
You should
guy,
have
for
asked
instance, like
Akshit because he
CS.
was in the
Actually,
lab while
both
those
of
things
them
were
have the
happening.
same top choice preference. They have the CS preference. And on the other hand, after the top choice preference, things go very differently. Actually, maybe in hindsight, they are a good example of what is it?
A low nutrient concentration, then species
So you
don't grow as much. They don't grow as much. They don't toxify the environment as much. And here toxification is by decreasing pH.
This one,
if you have a large nutrient concentration, and species grow a lot. During that process, they produce a lot of things like acetate.
They were not able to tell
that lower the pH.
one of those
And
three
this
nutrients
pH generically has
all
positive
of
or
them
negative effects on lots of species. So
in our
the pH
study,
mediated way, there is one understanding.
We tried,
now, there's a big sort of,
we tried to
I would say a big sort of debate in the lab about
system.
whether in this paper that's the mechanism.
Everything, so we had to improvise
but I will not
so we had to kind of assign those rankings.
I think the interesting point is indeed that probably this is more to do with
and
toxicity than with resource competition. I think from resource competition, you might expect
they are from,
who knows what.
From the gut. And
anyway,
the point we wanted to make is exactly the point that I wanted to.
It's not obvious at all that this thing, this phenomenology has anything to do with randomness. If you
happen to have the bugs,
it could be all about
the complementary top choice preferences,
interact with pH.
They will be much happier,
ways,
and we somehow translated
it's
happiness to their
abundance.
abundance.
A real smoking gun.
So this is our
kind of this proves that random
reality
something about this high-dimensional interactions, randomness of interactions is really what's happening here. What I'm saying is it's the closest
so our
anyone has seen, as far as in my opinion,
to with the top choice complementaries, they will be happiest.
In
if you have them randomly,
community ecology, in microbial community ecology, that would reasonably be
will make them all kind of
in this random
conflicting. If all of them
will
choose the same top choice, the same second choice, then they will.
Those are other experiments that I will not talk about for in the interest of time, but
kind of. Oh yeah, I have
you can actually go into
a story which will
stability
just help me fill the
there are things we can talk about.
I wanted to talk about control because I announced that my title that I am, you know,
I'm going to be very quick on this
bioengineering department. So when I want to pretend that I am a bioengineer, I'm saying, how about we control?
Lots of
because bioengineers always want to
were about
control
free
everything.
species, and not of the talks were about
physicists want to understand, but bioengineers
the real world is neither.
So
both are simple, right?
In fact, the
interesting
story here is that people who studied the control theory, in particular, well, the control theory is a mature discipline in mathematics and in engineering, but then a bunch of physicists, including Yang Liu, who was actually a student at UIUC,
in many cases,
was a postdoc in Barbier lab, and now
network can be somehow approximated reasonably by a combination of simple order. Let's say there are 4 trophic levels plus randomness within each of the trophic levels.
When he was in Barbier lab, he sort of applied the idea from the control theory, how you control a graph.
Yeah, I'm not going to go through this.
It turned out that if you have a graph,
sorry, Matthieu, what was
the control theory, if you want to control a graph, you basically need to, like this, for instance, the graph, you want to divide nodes in a graph into
initially, I was planning of doing a paper like this,
and you need to make sure that those pairs do not have the do not have the
when would you
any shared nodes. So you want to basically break up the graph
because if basically what I'm saying here is
collection of pairs,
a complex network is just
pairs
like
of nodes,
random structure plus some noise
you are not allowed to
and nothing
do
else
the
is
same
happening.
node in more than one pair. And of course, the pairs need to be connected by linking networks. The network is controllable
has the scaling of 1 over S or 1 over square root of S.
This is remarkably
the interactions between
this kind of
randomness and structure
because you
are very limited They don't do crazy things,
marriages
crazy
out of
things
all
together.
possible. Just imagine that those
they do one thing together,
pairs which are not connected, they are just somebody who hates each other so much that they will prefer to remain single than to get married.
From a point of view, in the spectrum of the matrix,
so
if you have
you may argue that if you are, and people
on top of it,
also talk about the optimal control.
So
sometimes you have a weighted network,
dynamics,
and the weighted network means that every edge has a particular number
spectrum is going to be almost not
and
changed.
if you want to find
the randomness is going to give you a bulk of eigenvalues.
Breakdown of a graph,
the non-random part is going to give you outlier eigenvalues.
Solve an optimal matching problem, which is find
in this
limits,
in this scaling.
Links on a graph, which has the smallest
number from the random part and the stability from the non-random part are going to be somehow non-interacting.
So this is
from the random part I could always get to this
chaos. Has been solved by nobody else but
from the non-random part I could always
get
to
this ordered. Parisi, of course, is a spin glass
so it's almost
Nobel
like
Prize winner.
You know, I can separate the things.
It is
this is actually true for the spectrum
of
the matrix.
Problem,
the problem
which
is
a
true for the spectrum of the Jacobian.
Of the stable matching problem
and that's the only trick
marriage problem. The only thing that they don't need to worry about, because as I told you early on, when you think about this problem as a physicist, you think about, you don't really worry about stability. When you think about it, the problem as an economist or as an ecologist, you always say, what if they don't want to live like this? What if the new species will come and outcompete this species? What if they will switch preferences and so on? So, and the interesting aside
so I'm wondering if the random interactions are of the order 1 over S and the sort of directed interactions are don't have that 1 over S, or do all of them?
To be stable, and found that the solution is roughly
interactions of order 1 with each other.
0.82
means that within the group, every species has an interaction of order 1 over S.
Pi squared divided by 12, so pi
the sum of all these interactions
like 9
still has to be a
non-infinite more than 9. Right? So 9 divided
for
by
one
12.
group to affect another.
What is important?
So in fact, you're still,
if you now think
saying
about, remember that I told you that the best stable
my group here, my
is square root of n.
Has an interaction.
So what if you are
with that
a dictator?
If
what
now
if you live in North Korea, where you can literally tell people to get married to whoever the dictator assigned them to, and nobody will dare to run away.
All of them together.
And what if you are a benevolent North Korean dictator who wants to assign the happiest, stable, unstable marriage?
What is the domain of validity of this scaling? That's what I want to talk about.
He will actually be able to get
everything I've told you.
Reduce unhappiness by about 18%.
Diffuse regime where
go down from the square root of n, which is unhappiness of a best stable matching, to the
square root of S
unhappiness of
the coherent part, whether it's just the mean or the structure.
Match.
The structure is just
so
like
that is
a matrix
kind
of means. Right? It would be a matrix of 3 means, a 3 by 3 matrix of means.
And now I think
so
4 minutes
the structure needs to have this 1 over
time to give you take-home messages. So
if you want to be in this well-defined thermodynamical limits,
I guess the most kind of unusual
you send S to infinity and you still have many
of the stable
yes, maybe I wasn't clear. So what I was thinking, you sort of talked about overlaying the rock paper scissors dynamics of 3 species with all these random interactions.
And the ability
so my question is, are those interactions involved in the rock paper scissors dynamics of a different order than all the interactions, all the random interactions?
So that's an interesting point.
So that is to me the most unusual thing that you can
individual
control and
this matrix. So it looks like a 3 by 3 matrix, but it's actually 1,000 by 1,000 threads.
And again,
this matrix here,
tomorrow I will tell you
another,
just to give you
if you look at what the mean
is, tomorrow's lecture
it's going to be actually, it has to be order 1 over S. Because it's the sum over all of them that will give you,
and a model will be about how microbes
so the thing that's very intriguing is structure,
essential resources, carbon and nitrogen, and it turns
even
out
though
that
the structure will be order 1 over S,
problem again will make an appearance in a particular variant of it, which is.
So if you were to look at the matrix, you would see only the randomness. You would not see the structure in there. The structure is very faint,
polygamous,
but on aggregate, since the structure sums coherently, it can create the fluctuations.
For the next. So
that's a nice thing. If I was going out in the world, I would see those interactions. I would see it would be like this is completely random, but in fact, it could have a completely structured or strongly structured dynamics.
The addition of nutrients allows the microbes to sort of coexist more, right? But this actually, if I compare this to Sarah's talk, and that's actually if you add more nutrients in that machine oil, then they start becoming competitive.
Yes.
I was wondering if
I'm just going towards the end of this from her talk. So she said that if you add more nutrients,
that's the point. The structure is going to be very hard to detect because
I didn't quite get this message from her talk. Maybe you're right, but
structure is going to be 1 over S.
her system is closer matched to what I will be talking about tomorrow, because
so I guess
what is quite clear is that
once you go into that world,
the
abundance distribution
factor
is very sensitive to adding order.
So two of your bugs are
much less sensitive,
which means they cannot synthesize
is actually
amino
completely
acids.
insensitive to
And it is quite clear that some of the
you're in a world where
unusual transitions in her community come from
the feedback. Even if you add structure, you're still in a world where the other species are like an environment for you. It's just that it could be a completely random environment or a slightly more structured environment.
Emphasizing that addition of nutrients
many species collective limit,
but it is
just somehow changing the environment for every species, but not changing its feedback.
No, in principle, it shouldn't happen.
So if I remember, it was adding amino acids
that leave you with this. Yeah, maybe with this. Okay.
Increased. Well, okay. That actually goes along with this.
A lot of other places where you could do biology.
Hold on to this question until the next talk I will
flux of birds,
and I have a perfect answer here, because this is exactly what happens when you have
in networks of interacting species.
The reason
in
why
ecology,
her community is
no one has really shown
diverse is because
without a doubt that there is a collective phenomenon.
An ecosystem-wide resource, and it's not a carbon resource.
We don't have yet any.
If you have this community with multiple essential nutrients,
to my feeling, no one has
making one side of the story flooded with nutrients.
It's not very clear what would be the collective observables and the collective structural metrics.
Well,
at least if you're in this order, then we know what the collective things are.
Were prevented from competing for carbon sources.
I guess that's one of the
by being limited by amino acids.
And maybe
once
in my
minus 1 minute, I just want to finish
suddenly
all those bugs
with the philosophical notes.
And
it will take me probably one slide or two.
Start competing for carbon and diversity decreases.
A lot of things here, but
this is a well-established fact. There are actually nice studies in some experimental field in England where over 40 years they were experimenting with adding nutrients to the soil, but they were looking at plant diversity.
Tiny part of my tree. Now I have the whole tree back. So thanks for whoever was asking me about
flood the soil with fertilizers, nitrogen, phosphorus.
This is
the whole diversity drops because
I spent some time talking about the first three choices.
Limiting resources, there are
next two choices are my cube,
which are limited. The growth limited by carbon, nitrogen,
and here I'm in this corner of the cube. I chose to talk about
not in
this
plants,
thing here.
but in the ocean it could be iron. Once you flood those essential nutrients, the effective number of nutrients for which the community competes is reduced.
Up to you to decide.
This is a little bit counterintuitive.
But at least
you add resources
there's a part of the
in
cube
concentration, but you reduce the number of resources
all of
for
this
which the
subset is reasonably well explored, and all of that, all the other part of the tree is very poorly explored,
through which the community
and so you can decide where you want to go.
So that is my interpretation of what is going on. I'm 95% sure I'm right in Sarah's
transition. Coming as a physicist into ecology, what are the reflexes?
All of them will start
of physics that really worked for me.
Carbon sources.
The atomist reflection doesn't work so well because we don't have good atoms.
Probably.
Most of the time, you cannot measure the parameters that we would need to have a very mechanistic.
They will all kind of fight for the same thing.
There's no strong conservation laws, no strong symmetries in the systems. Maybe the only symmetry in the sense that really matters across ecology is this symmetry of saying that reproduction matters for everybody, which is basically saying I have equations where dn over dt is increased somehow proportional to
Jacopo.
It's a kind of symmetry, maybe if you want to think about it.
What happens with the lag
you don't have many symmetries. Empirically,
you could apply the experimental physics methods of saying, I want to understand the system, I'm going to shine a laser on it from various directions and I will do the crystallography of that system, right? The problem is, when we do experiments in ecology, if we perturb the system from different directions, we have no idea what the perturbation is really doing to the system, we don't have the intensity of the laser, so we cannot really extract maybe your second and third choices will
very, very hard.
So the amount of resources you will effectively utilize will be reduced.
Typically,
you will become maybe not a specialist,
what would be realistic ingredients and making a soup of them.
You will only have a chance to use your resource number 1 and resource number 4 because 2 and 3 will be eaten
and it doesn't really help you. So I guess the one thing that for me really works,
which is
that I get away from coming as a physicist
may increase diversity, but in a
into
boring
this
way,
field was this kind of minimalism and universality that would probably speak to Sergey. The zero parameter type of thing is
really boring.
Maybe you will find other things. That's for me the theory part of things. Now for the modeling part of things, maybe more of those things you could transfer. But for the theory part of things, you shouldn't be too naive about which of your reflexes are going to work if you work on ecological systems. And I think I will leave you with just the credits to the many people who have participated in building up some of the materials, which are basically like schools happening at INTP, which is our little science ashram in the French mountains. And so, yeah, many thanks to everybody who brought ideas to this. And I take responsibility for all, of course, of the errors that I added on top. Thank you. And so, yeah.
Yeah, regard to the scaling and therefore the applicability of results and the phase diagram, I just wanted to understand. So this scaling means that your self-interaction is S times stronger than the interaction with other species, right?
Yeah.
Is that right?
Yeah, it's perfectly correct.
Okay, and therefore, when you're working with this scaling, you're working in this yellow region, is that right?
I'm working in this red zoomed out part.
I see, including the chaos part.
Including the chaos part. I showed you the derivation for the yellow, but you can actually do it analytically for the chaos. And I would interpret this as the only region in which you would have collective phenomena. Because if you go to much higher interactions, then in fact, you start having few species surviving. You're not in the collective region anymore.
Yes. So, one maybe, one can expect that, as an ecological species, you might have weak interactions with lots of other species that are there in the ecosystem.
Yeah.
But there might be a few other species, order 1, order 2 species, order 10 species maybe, or, with whom your interactions would be strong.
Yeah.
Now, is that then, so those will be, comparable to your self-interaction. After all, bacteria might depend upon what other bacteria are producing, toxins or food, etc., and whatever else.
Sure.
Species providing shade to other species or nutrients or whatever. So in that, is that the regime in which you go into the purple?
So if you were just looking at the interactions between those three, you would be more into this orange or purple. Now they do not have any reason to be random anymore, right? If there are only a few interactions, they might be very non-random. But I would say combining many weak interactions with a few strong is another way of combining simple structure with randomness, or randomness with simple structure. It is also perfectly valid. And it's another direction in which we've tried to push a bit these ideas. You could ask, for instance, in that case, do you have that the interactions between those three species are kind of decorated by all the randomness happening around? And that's kind of how it works in some limits. You can understand these kind of things, yes.
Each species has a set of 3 other species or 5 other species with which it has random interactions, and each of those species has another set of 5 other species with including this one.
Right. So then it's a sparse network.
It's a sparse network.
Yeah. So the sparse limit of random networks is also something that you can deal with. The problem is it's less universal than this. So either you have many interactions and they're all weak, or you have few interactions and they're strong.
Yes.
You could still have a random network and you could still do analytics. But now the analytics are more sensitive to the details of the model. You could have very different dynamics if you're below or above some thresholds in the number of interactions. You could have a lot of things are going to depend more, right?
So has that been worked out? I mean, those kinds of things?
Yeah, quite an amount of a number of those things have been worked out. It's the sparse case. It's just in a sense I have fewer general conclusions about it. Mm-hmm. Like for instance, if the interactions are completely symmetrical versus a bit symmetrical versus asymmetrical, you can get very different properties in the sparse world. Whereas only the purely symmetrical case is completely unique in the dense world.
So what's the? I think I missed the. This is a bit late. Missed the references that you might have given for today's talk, and references in which these are the sparse matrices, etc., that you just mentioned.
Oh yeah, sure. So I didn't put any references for sparse matrices. You should go look at the work of Bunin and Marcus. So, okay, for most of these things, just read the entire bibliography of Guy Bunin and you're probably about right. Most of what I do is translate Guy Bunin. into ecology. That's
what's the difference?
So I don't. There's several of them. There are recent papers by Bunin and Stav Marcus, who is a PhD student or finished maybe of Guy Bunin, and I think he might have a few other references about sparse systems. But yes, if you look at Marcus and Bunin, you'll get some of those sparse things. He's not the only one to do that, of course, but he's the one that I know best, and I think he has covered. It's the closest to the kind of things we're talking about here.
And this phase diagram stuff?
Yeah, this phase diagram is in Bunin 2017, at least this part. So Bunin PRE 2017. I can almost quote the sutra, you know.
This URL doesn't work.
My what, sorry?
No, it works. It's case sensitive.
No, it got loaded up.
Okay. All right. Let's thank Matthieu for a great set of lectures.